we're going to just start with that definition of sequential compactness. And this is how Tao defines compactness. He only defines this version, which is very non-standard. Okay, so take a metric space. And then take a set. We'll call it K inside your metric space. And that set is sequentially compact if and only if every sequence in that set has a limit in that set. Oh, sorry. Every sequence has a subsequence that converges. Okay. Let me let you think about that for a second, and I'll be right back. Okay. Does this definition remind anybody of anything? Yeah. It is like Bolzano-Weierstrass. Now, what did Bolzano-Weierstrass say?
In real numbers, every sequence has a convergent subsequence.
Not quite every sequence.
Every closed and bounded sequence. Right.
Every bounded sequence.
Rebounded, okay. Mm-hmm. Wait, closed doesn't make sense. I'm sorry. Why am I saying closed? Right?
That's fine. So,
yeah.
So Bolzano-Weierstrass said every bounded sequence in the real numbers has a convergent subsequence. Well, we're going to prove that compactness and sequential compactness are the same. We know that every closed and bounded subset of the reals is compact. So after today, we'll know that every closed and bounded subset of the reals is sequentially compact. And that's Bolzano-Weierstrass. Okay, so this is a pretty powerful, well, we just have a definition, but anyway. This definition is capturing the behavior in Bolzano-Weierstrass. Okay? And like I said, this is Tao's definition of compactness, but that's weird. I've never seen anybody else do that. Okay. Okay. The other thing we should note about this definition is that it is intrinsic in the way we've been using the word intrinsic. So we use intrinsic to mean it only depends on the set K and the metric. What it doesn't depend on is the ambient space X. Okay, you can see that there's no dependence on X in here. Whether or not it has a subsequence that converges in K, it doesn't matter what X is. Okay. Here's a consequence. If you're a sequentially compact set, you're also complete. Why is that?
Well, if every sequence has a subsequence that converges. We have I think maybe it was a homework problem or something that we did that was that if a subsequence of a Cauchy sequence converges, then the Cauchy sequence converges also.
Yep, that was the question on the last quiz that I had to throw out. It was on the last quiz, but I promised you we wouldn't have Cauchy sequences on the quiz, so I had to throw it out. But anyway, that was the problem on the quiz. So let me write this in real quick. This is sequentially compact implies complete. Okay. Take a Cauchy sequence in a sequentially compact set. It has a subsequence that converges. You can show that if a subsequence of a Cauchy sequence converges, then the Cauchy sequence itself converges. And that's what completeness is. Every Cauchy sequence converges. Okay? Now, we want to prove this is the same as compactness. So, we're going to do this in the two obvious parts. First, we will prove every compact subset of a metric space, really. I mean, I could just say compact set. Is sequentially compact. Okay, so let's just think through what we're going to end up doing. We're going to take a metric space. We're going to take some compact set in there. And compact means every open cover has a finite subcover. And then we're going to take a Cauchy sequence, not a Cauchy sequence, sorry, just any sequence in there, and we need to find a subsequence that converges. Okay? And it's almost a straightforward proof, except we have to look at things a little bit weird. So let's see. So the setup, we're just going to take a metric space. And we're going to suppose we've got a compact set in there. Okay. Now we need to get our sequence. Sequence has to be from K, and remember, by that we just mean that every element of the sequence is in K. Okay. Now, we're going to make a definition that it's a set that we haven't really looked at yet. I mean, a set that we... I know it's an idea that hasn't really come up yet. Oops. What I want to say is for any epsilon and x in. Okay, given an epsilon and a point x, we're going to need to look at it's almost, I mean, it's sort of the epsilon neighborhood. But what we want to look at is the set of indices that get us within epsilon of x. So this would be the set of indices where that term of our sequence is within epsilon of x. Okay. Now, these aren't neighborhoods. These aren't like open sets. I mean, these are subsets of the natural numbers. So there's no topology here on these sets, okay? All we're going to be talking about with regard to these sets is whether they're finite or infinite, okay? So let's just think about it this way. If we did have a limit of a subsequence, say there's my point x, it's the limit of a subsequence. Well, what would you see? You'd see that subsequence would be getting close to x, right? Arbitrarily close to x. So in fact, what you'd see, the subsequence has infinitely many terms. For any epsilon, you draw this little epsilon ball centered at x, you would see infinitely many terms of the sequence in that ball. So if a subsequence converges to x, then I epsilon of x is infinite for every epsilon. Okay. Any questions so far? Are you with me?
I'm just a little confused. Maybe not confused. I'm just a little like this picking out the indexes seems really strange. Like it seems like something I don't know. It just kind of rubs me the wrong way. Like a spider sense is tingling. Like this doesn't feel right. Is there like something that lets us do this, or is this just something I've never thought of before?
Oh no. That's a good question.
No.
Sorry, 1 second.
I want to get more use.
Okay, give me a minute. Okay, so here's what you would like to do. You'd like to talk about the terms of the sequence, right? You'd rather talk about the an than the n. Is that right?
Yeah, it feels weird to be able to first to choose, like to take all of these ANs in here and then somehow magically know what their index is.
Yeah. So the problem with talking about the points of the sequence is that the sequence could be eventually constant or something. And then there would only be one point in the sequence. So, I mean, it's a key. Look through the proof, and you'll see why we had to do it this way. And the reason is because we need to talk about indices because of repetitions in the sequence. Okay? Because of possible repetitions in the sequence.
Okay, so the indices are just eliminating repetitions.
Yeah, well, it's not eliminating them,
How
but
many
it's...
terms, and if they're all the same, then it falls apart.
Yeah, so consider your sequence minus 1 to the n. If we're going to start talking about just the points in that sequence, there's only 2 of them. Right? And that's not going to go well for our arguments. We really need to think about the number 1 in that sequence as occurring infinitely often. Okay? Good job. Okay, here we go. It's going to be 2 cases. One case I'm going to show you it can't happen. So first, suppose that all of these sets are finite. Well, I'll just write it out. First, suppose that for every x, there is some epsilon, and I'll write it as epsilon sub x, just to make clear that it depends on x, such that this set of indices is finite. Okay, now think about what I said over here in the yellow. If a subsequence is going to converge to a point x, then all these sets are going to be infinite. So here we're saying, suppose that actually for every point, we can find a small enough neighborhood that only contains finitely many points of the sequence. So if this held, then there would be no point that a subsequence converged to. Okay, so we need to rule this out. Consider the family we're going to look at the open ball centered at x of radius epsilon sub x. For every point, I don't mean x in x. I want every point in R compact set K. This is an open cover. Why is it an open cover? Well, every point's in its own epsilon K neighborhood. And we've given a neighborhood for every point here. So it's clearly an open cover. It's got every point in K in it. So since K is compact, we've got a finite subcover. So what would a finite subcover look like? Well, it would be finitely many of these sets. Okay, so that would mean we'd have finitely many points x, such that our finite subcover consisted of the neighborhoods centered at those points. So there is some finite subcover. Oops, and that's what I want to write. There's some finite subset. I'll call it F, such that actually if we just take the balls centered at those points, that covers K. Okay, but this is a contradiction. So these finitely many neighborhoods would cover all of K, so they would contain every term of our sequence. So for every index, n in n, there is at least one point. Well, let me write this and then we'll talk about it. Such that n is in I so epsilon x of x. What's going on here? These sets cover K. So every term of our sequence is in at least one of those sets. Okay, now let's, instead of looking at the sequence terms, let's look at their indices. That means that for every index, the term a sub n lies in one of these balls. That means that the index n is in this capital I set of that center x. Okay, so the first two things that I've highlighted here are, thinking about the points of the sequence, but then we need to think about the indices. And the reason we need to think about the indices is that points of the sequence might be repeating. Okay, so I can't say that like infinitely many, this is precisely to Daniel's question. What we cannot say is that infinitely many of the terms of the sequence are in one of these balls, because it might not be infinitely many terms of the sequence, because all the terms might be the same. Okay. Well, okay. So the point is that there's infinitely many terms, infinitely many indices. Each of them lies. Each of the indices lies in at least one of the sets I, but we assumed that all of these sets are finite. That is a contradiction. Okay. So let's see where that contradiction gets us. Okay.
Can you repeat why that's a contradiction again?
Mm-hmm. We have assumed that each of these sets is finite. But there's only finitely many of them, because F is finite and we're only looking at the ones where the center is in F. So we've got a finite union of finite sets. But on the other hand, the set of indices is the natural numbers. So we're not going to get the natural numbers as a finite union of finite sets.
Okay, thanks.
Mm-hmm. Okay. So now, what have we contradicted? We've contradicted our assumption up here in red, that for every x, there is some epsilon, such that this set of indices is finite. Now we have to carefully negate that. What does that mean? That means for at least one point, there is no such epsilon. So having no such epsilon means for every epsilon, that set is infinite. Therefore, for at least one point, x in and I realize up there, I'm sorry about this, we wanted that x up there to be an x in K. Okay, for at least one point, x and k, well, this set is infinite for every epsilon.
Oh, tail. Tail. It's tail.
Okay. Now, think about a picture here. There is some point x, so that no matter what radius you draw, you look at a open ball, but it doesn't really matter here, you're going to see infinitely many terms of your sequence in there. Okay? And then you draw an even smaller ball centered at x. You still see infinitely many terms of our sequence in there. Okay? I hope you're convinced that that should mean that we've got a subsequence that converges to x. Okay? And now it's just, okay, well, technically, what do we do to actually prove that we've got that subsequence? Okay, so what I'm about to do is basically like it's a standard exercise in kind of sequences. And we could have done it, back at the beginning of the semester when we did our lecture on sequences. This could have been an exercise. But how do we do it? How do we get our convergent subsequence? Let's choose our indices n1. N1 doesn't really matter, but we'll make it so that the distance between a sub n1 and x is less than 1. Okay. Now, we're trying to build a subsequence. Just remember, our indices have to strictly increase. Next, choose an n2. But n2 has to be greater than n1. And let us choose it so that that point is within a half of x. And now we just have to think about why we can do this. The set of indices such that the corresponding points are at distance less than a half to x is infinite. So there are infinitely many indices so that that term is within a half of the thing we're trying to prove is the limit. So since there are infinitely many of those, there are also infinitely many of those that are greater than n1. So we can always do that. And I hope you see the pattern. I'll do one more. Next, choose n3 bigger than n2 so that the distance between our a sub n3 and our hopefully limit is less than 1/3. Okay. And now we just kind of say, continuing in this manner, what do we do? We construct a subsequence, a sub n sub k, that converges to X. And that is all we needed to do. There we go. Got the whole proposition on there. Although it is a little tiny at the top. Let me again emphasize that what we did at the end of this proof is kind of a standard result about subsequences, and it's something you might want to keep in mind because it does come up. There are other times where you might want to use this. Okay. Okay, what questions do you have?
I got a question about this, the standard exercise thing.
Yeah.
So here we're choosing elements that are indexed on the natural numbers instead of on the reals. Because I know there's like a difference between choosing. Because I'm thinking about like I know Tao always mentions like when the axiom of choice is being used. Is this one of those scenarios?
Yeah, it is.
Okay.
Anytime you make infinitely many choices, that's an axiom of choice. Well, there are a few exceptions, but generally when you make infinitely many choices, it's axiom of choice. And this is certainly axiom of choice. Right. Okay, so Ben points out in the chat that, yeah, we didn't quite dot all our I's and cross all our T's at the end of this proof. Because what we did, I just asserted that this subsequence converges. But now we're at the point where that's fine. This is a subsequence where its terms are getting, its nth term is within 1 over n of x, so it converges to x. But yeah, if you have to write out that proof, then let epsilon be given. There is an n, so that 1 over n is less than epsilon. So therefore, for all the terms after that, you're within epsilon of your limit. Okay? But yeah, that's officially okay now if you find a subsequence like this where you're within 1 over n for each n, then you're good. Okay? Other questions?
So with this half of the implication, we now have that every compact set is also complete.
Yeah. That's actually the next result in the notes. So what we have, sequentially compact implies complete. We did that at the beginning. That was the subsequence argument with Cauchy sequences, right? So now we have another result. I'll just put it up here. Every compact metric space is complete. Okay. And given what we've established, there's absolutely nothing to prove there. If it's compact, it's sequentially compact, and if it's sequentially compact, it's complete. So if you've got a compact space and you've got a any sequence in it, it has a subsequence that sorry. If you've got a compact space and you've got a Cauchy sequence in there, then it converges. Okay. Now, does that prove that the real numbers are complete? Does this prove that the real numbers are complete? Because we know the real numbers are complete. That's remember, that's an axiom. Yes. We have the answer in the chat. The real numbers aren't compact. But still, can you get the completeness of the real numbers out of the stuff we've done today? So let me just, where are we here? So my claim is we still get the completeness of the reals, even though they're not compact, based on the stuff we've done.
Is it not based on that we can construct the reals from the rationals by completing them? That's like a little cheat, right?
That is, okay, so what Daniel's talking about is true, and we've talked about it. That is well beyond anything we've done, though, if you think about it. Right. We haven't constructed the reals as the completion of the rationals. So I claim we can still get this as a corollary. And how would we get that? Well, completeness means every Cauchy sequence converges. So let's let AN be a Cauchy sequence. In our metric space. Now, if, Benjamin has it, yes. So this is the thing. If we could say that AN were a sequence in a compact set, then we would be done, because that set would be sequentially compact, and therefore complete, and therefore AN would have a limit. Well, we know that every Cauchy sequence is bounded. Okay. I'm writing every, just to emphasize, this is a thing we know in any metric space, it's bounded. This was, I believe, the last lecture that we proved that, right? Or maybe two lectures ago. thus there is some radius r greater than 0 such that, well, every term of our sequence is between minus r and r.
Move, guys. There you go. Move. Move.
We know that the closed interval from minus r to r is compact.
What are you gonna do here? Now you. Now you guys say you.
So it's sequentially compact.
Gary, boys, are you in trouble?
Okay, we don't need your commentary on this. So it is complete. So our sequence converges. And in fact, we know that it converges in this particular closed and bounded interval.
The monsters.
Does that make sense, that proof?
Oh, guys,
So we're taking
go on.
like local compactness makes
Going.
it gives us the whole set is complete.
Yes.
Daddy, Peter.
So that's a good word for it. The real numbers are not compact, but as soon as you can bound anything,
What?
they are. Right? They're almost compact, because as soon as you can get your thing in a bounded set, you're done.
Yeah.
Okay. I had foolishly thought that we're going to do both halves of our compactness is the same as sequential compactness today. Obviously, that's not going to happen. We'll do the other half on Monday, and that will, I promise that will actually be the last lecture on compactness. And like I said, the quiz on Wednesday will be compactness, and then it's going to keep coming up throughout the course. So we were never quite done with compactness, but okay. So for our final thing today, I know, why don't you go check it out? Sorry about that. Our final thing for today, would anyone like to criticize this corollary? Because there's a very real sense in which this corollary is kind of stupid.
Well, haven't we just assumed from the very outset of the definition of reals that they are complete?
Yeah, we assumed the reals are complete at the beginning of the course last semester. And the way we assumed they're complete is we assumed they had the supremum property, right?
We've used that in our proofs, right?
Yeah. So what did we use the supremum property to prove?
That the closed and bounded sets are, what do you call it, compact.
Yeah. So, in some sense, well, I mean, in a very real sense, this is just circular logic, what we've done with this corollary, because we used completeness to prove that closed and bounded sets are compact, and then we turned around and used that to prove that the reals are complete. Okay? So that's...
Well, maybe if we don't want to feel so phony, we can say the supremum property implies completeness, and that maybe we can be a little happier with that.
Yeah, although, I mean, we've kind of been saying that they're the same thing the whole time. And there's easier ways to show that they're the same thing.
Here's the yellow.
I think the value of this corollary is that we took this big journey all around, right? And we saw a bunch of stuff, and we ended up right back where we were because it was circular logic. But everything you can see how everything's kind of fitting together, right? So sure, this only proves completeness if you assume completeness from the start. But it's not quite as stupid as that sounds, right? Because you see how everything fits together. Okay.
I think that this proof is nice though because it's showing that the circular reasoning is that those sets are compact, but you can sort of abstract that and say that this local compactness has implies completeness, which I think is pretty important, maybe.
Yeah. So I mean, that's my thesis. Despite the circular logic here, this is a nice result because it shows how all the pieces fit together. Okay. Well, let's stop there. I guess Monday we will finish. We'll do the other direction, and then maybe we'll do some examples, so we don't have to do new material. We don't have to start a new topic on Monday. So we'll finish up the compactness. I'll stop the lecture here.